just a reminder that we were calculating for the assignment number 3 the inviscid version of the Burger's equation in just one dimension, and we do have two ways of calculating the Burger's equation. One is the non-conservative form, where you have u du dx, and the other one the conservative form. Remember, the conservative form of the equations have everything inside, all of the everything inside is the gradient operator for the spatial derivatives, which is obtained by writing this flux term as u squared over 2. So what else? We can write this equation as we also write du dt plus a matrix A. The general is a matrix. In this case, this matrix only has one value, u, right? Du dx, but our schemes are general, so in this case, A, which is a function of u, is called the Jacobian. So this applies to other equations of this form. For Burger's, of course, it's very simple. The Jacobian is simply equal to u, but we can use the same approach for other equations. Now, this is in general a matrix, so if you have for more than one dimension, A will be equal to basically the derivatives of the flux term with respect to the different components of the independent variable. That's in general. In this case, for the 1D matrix, it's just df du. That's it. So just as a couple of reminders about this system, the equation is, or system of equations, if you have more than one dimension, is hyperbolic, right? And for hyperbolic equations, one can, what does it mean, the hyperbolic equation? It means that all of the eigenvalues of A are real. Of course, in this case, it's just u, one value is real, so no problem. But this is in general for more than one dimension. And so for hyperbolic equations, one often distinguishes between two types of solution. We call a strong solution trying to just use the simplest words possible, is a solution that is continuous, but you can have some bounded discontinuities in the derivatives. But the solution is continuous, whereas a weak solution is a solution that is continuous almost everywhere. So it has a jump, like the case that we've used for this assignment, right? We have a jump of velocity at a given point, just a one jump. So these concepts do appear quite a bit in the literature, so I just want to make sure that you have you've seen them. They will appear in some of the, if I give you some of the papers that go with this material, they will appear. So this is a solution that is continuous almost everywhere. So it has a jump. Like the case, the shock wave, right? The case, this, for example, for Euler equations, a shock wave. And this is the situation we have for this assignment. So we're solving for a weak solution in the assignment. So let's now see. Let's go straight to the different cases that we saw. The 5 different ways that we solved the initial condition, which was just a jump from 0 to 1. Okay, so this was a step 1. We just solved the Lax-Friedrichs scheme, solved this problem, the Burger's equation with the Lax-Friedrichs scheme. Our test problem is simply a jump at point x equal to 2. So notice that our stability condition was written in this form, where U max is really, if you want to generalize this, for example, to 2 dimensions, then this value U max would be the maximum eigenvalue of the A matrix. So you could, in this case, A matrix is just A equal to U, so there's no, there's only one eigenvalue, U. In this case, the A matrix has a single eigenvalue. So remember that with each computational step, the information travels delta x. So the computational speed at which information travels is delta x over dt. So the meaning of this stability constraint is that, the velocity u has to be less or equal than delta x over delta t, where this delta x over delta t is the velocity. This is the velocity at which information travels. Let's call it just the computational information. So our interpretation of this was that the solution itself must not move faster than we can move the information in the computational scheme, right? So if we were to now, we're going to use this. I'm reminding you of this so that we can discuss the solutions that you saw when you programmed this. And of course, we know that the method is first order, so it's distributive. And so if we were to calculate this solution with, say, the delta x and delta t that I gave you, delta x equals 0.1, delta t 0.1, so that CFL is equal to 1, and we look at the solution at 3 different time values, then you would get something like this, where the initial condition is given by this dashed line, and we are advancing the shock towards the right, and the shock itself is being subject to numerical dissipation. So the shock is smeared over several grid points, even though at time 0 it was just one grid point, right? So let me just clear the annotations so you can see it better. So that is looking at several time steps for a given chosen CFL number. Now let me show you the same, which you must have obtained, with the same value of delta x, but with varying CFL number. Okay, and this is what we see, 3 different values of the CFL number. So one of the conclusions that you see here is that, so notice here I've indicated that this is the same final time, so the location of the shock is at the same point, and the dashed line again is the exact solution, and for the same value of the mesh spacing. So what the effect of varying the CFL number is that more time steps are required for the small CFL number to reach this final time, and so there's more numerical diffusion, right? So you see that as you decrease the CFL number, the shock becomes more smeared, and the solution is of worse quality because of the numerical diffusion. Fine. This is, you all agree, you saw that, or it's this is one of the take-home messages of looking at different CFL numbers, that there's a decrease in the quality of the solution for smaller CFL numbers. Now, what happens if we vary the CFL number? Remember, this is our limit of stability. So if we go anywhere above 1, then we should get unstable solutions. So if I run this with these 3 values, 1, 1.5, and 2, this is what I get. So this, with CFL above 1, the solution should go unstable. So what's happening here? Let me show you, actually let me show you this in action, because I got the code right here. Actually, this is my Lax-Friedrichs right here, and I can run it with, I've got the code repeated 3 times, so I can run it with 3 different CFL numbers and plot them at the same time. So I'll run them with 1, 0.5, and I have a little further below the same chunk of code repeated with sigma 0.25, so I can plot them all together. Maybe there's a better way of doing this. Friedrichs. This is the solution we're looking at. And this is how I generated that plot that I've just showed you with the 3 values of CFL now. So no news there. Now I'm going to change that to, say, I'm just going to leave that one at 0.25. I'm going to change that one to 1.5. And I'm going to change that one to 2. So all of those greater than 1 solutions should become unstable. So run it. And here's my result. Right? So really by my CFL condition, my stability condition for this scheme, I expect this to become unstable for any value greater than 1. Yet here's the solution with CFL equal to 2. What's happening there? Anybody have a guess? Let me go back and notice something that you could have seen with step 1 of the first assignment, which was the linear convection. With the linear convection, the u dt equal to minus c du dx. The Lax-Friedrichs scheme would have given me, well, let's just look at the usual one actually. Let's just look at our usual one was un plus 1 at I minus un at I divided by delta t equal to minus c and u n I, what is it, ui minus 1 and ui? No, ui plus 1 and ui. Okay. Over delta x. That's a usual one, right? So what happens if we chose for this case, this was step number 1, right? For step number 1, so in other words, I can write un plus 1 I equal to uni plus c delta x over, no, sorry, delta t over delta x times un I plus 1 minus ui. So let's see what happens with the CFL equal to 1. Let's see what happens with CFL equal to 1. That means this thing is 1, And so this guy cancels with that one, and we've got an exact solution. This is what I wanted to just... We've got that u at I plus 1. This is what I... So the solution is going that way. So this should be I minus 1. So this is why I've got it wrong. It's I minus 1, right? I'm doing this from memory and I got it wrong. So if the solution is going in this direction, okay, the linear case, and we take CFL equal to 1, this cancels out, and we're only left with the fact that the point at I, n plus 1, is simply the point I minus 1 at n. It just moves one time step. It just moves one, the whole thing just moves to the right 1 delta x. So the solution is exact. There's just cancellation of errors, and the solution is exact with CFL equal to 1 in the linear case. Now, so in the nonlinear case, we have for Lax-Friedrichs, we have u n plus 1 at I is equal to, here we do the Lax-Friedrichs trick of doing the average, u n I plus 1 minus plus u I minus 1 n. So this is the average, which is equivalent to u I n. And then we have the term, which is the nonlinear term, where we have used a standard difference. So we have delta t over delta x times uni plus 1 minus uni minus 1 over 2. No, is the square of these things over 2. And let me just write the 2 separately so it's clear where they come from. Each one of these is the flux term. Right? It's a 2 out here. Thing. Okay. Now we're good? Okay, so that's the Lax-Friedrichs. So what happens when for our particular test problem, this is a very particular case where we have the value 1 and the value 0 everywhere else. At every point down here, right, you're going to have that the velocity at the 2 points is always equal. So this is going to cancel out because these two values are equal. So it cancels out, and this is just the average of 2 points that are the same value, so it's just the same value. Nothing happens. The only possibility of these two being different, because that happens here, it also happens down here, is when you're at the shock, right? At the shock, you could have that one value, the value at the right-hand side is 0, and the value at the left-hand side is 1. That's the only possibility that these two values are going to be different, right? Then you have, when we've taken CFL equal to 2, this one is equal to 2, cancels out with this 2, okay? This is 0, this is 1, this is 0 squared over 2, this is 1 squared over 2, and we have 1/2, and we have here, it's a plus, so this is also plus 1/2, which gives me just equal to 1. Good? All right. So it means that at the next time step, the value, whatever value, suppose this is I, and this would be I plus 1, and this is the value that has a difference, this is going to just jump from being 0 to being 1 at the next time step. And the same situation will repeat the next time step. In the meantime, at the next time step, the shock has moved to the right, and the shock is moving. So the shock, for your information, the velocity of the shock is equal to, the shock conditions are that this is equal to the average of u right plus u left. So the shock is moving at the velocity of 1/2. Our CFL is equal to 2, So the CFL is just moved past delta x. And then the next point is going to be at the same situation, where there's just a precise cancellation of terms such that that point jumps from velocity equal to 0 to having velocity equal to 1. Whereas every other point suffers no change. You see? So this is just a complete coincidence of cancellation of terms that happens for this very particular test problem with CFL equal to 2. It's just not general at all. If, in fact, I were to, so let me show you again my code that I have right here. And let me suppose that we change here, and instead of having the shock being 1, I change it to, say, 1.1. So just move it so the shock has a little different speed. Okay? There's going to be no cancellation of errors in this case. Let me change it for both. So I've got two solutions because I used one, I believe. I used this auxiliary variable, so I can change the one. This is just the value of the solution between 0 and 2, right? And I'm changing that to 1.1 instead of 1. And I run it. And now it's completely unstable, like it should be. It is supposed to be unstable for every value of CFL greater than 1. So you were misled to think that CFL equal to 2 was the best solution if you tried that value. You ignored completely the fact that I told you that it should be unstable for any CFL greater than 1, and you decided this was the best case, right? Some of you selected that, and you said, you know, Lax-Friedrichs and Lax-Wendroff, they're all just with CFL equal to 2, awesome, they're the best solution, right? Technically they were. Yeah, they were the exact solution indeed.
I said if you get the CFL equal to 2.
But the thing is, if you change your initial condition to anything different, it will not happen. This is also a good take-home message that CFL, the shock becomes worse as the CFL decreases. Now, you have to understand why this happens, because you sometimes see, like if you go to like CFD online and there's students discussing things, you'll see people saying, I've heard that, the numerical schemes are worse with the CFL number, with smaller CFL number. But they don't understand why, and they just say, okay, lower CFL number is lower accuracy, and this start extrapolating that rule as to apply always. And if you understand why we're saying that, then you will know that it's not a general, it's not a universal rule that you can apply to every scheme. It applies to the first order schemes in this situation here, because to get to a given time, you are just time stepping, you're doing many more time steps if your CFL is smaller with the same mesh resolution, right? So that's why you see this. The solution becomes worse as the CFL decreases. For a first order method with numerical diffusion, this is just accumulation of numerical diffusion as you time step. Okay, we've explained that. So the best behavior for this scheme really is CFL equal to 1. Above 1, it becomes unstable. So you have to live with a small amount of numerical diffusion and the staircase pattern, of course, produced by the odd-even decoupling. If we go to Lax-Wendroff, then we see this is one of the, by the way, Lax-Wendroff was one of the first second-order finite difference methods that was introduced historically for hyperbolic PDEs. We have the same stability constraint. Okay, and we see in this case that the shock is much more sharply defined than the Lax-Friedrichs. Because it's a second order method, we have a much better shock, but we get these dispersive errors, right? The oscillations, these overshoots that appear here. Dispersive nature of the method becomes evident. We looked at the behavior of the error for different wave numbers. And we saw, for example, if you recall, there was we called the errors, we had a epsilon d for diffusion, and we have an epsilon phi for dispersion. And this one, we showed some plots, and we showed that the error depended on the wave number, content of the solution. And I even had a couple of samples that would calculate, an initial condition of different frequency content, and we saw if the frequency content, if there was a higher frequency content with a given scheme that we showed, you would get much more dramatic diffusion of them. And what else we saw? The case of the numerical velocity being different than the physical velocity, and we had lagging error or leading error. Remember those ideas? So what happens is if you have different contents of wave number in the solution and they're moving at different speeds, they're kind of torn apart, right? Some wave numbers will move at different speed than others, and this is what you're seeing here. You get the waves appearing, those oscillations. Those are the concepts that we need to bring to bear in this discussion. So do have a quick read over your notes back then, or you can quickly review the video on iTunes and sort of advance the time to that little bit and just listen to those 5 minutes to remind yourself of the concept. Now, in this case, if we change the CFL number, we will see that there is also a difference in how the dispersive errors behave with different CFL numbers. And so notice the same final time, and the same mesh refinement, but different CFL. Okay? And we will see that as CFL decreases, the oscillations are bigger in amplitude. They're more pronounced. So the solution deteriorates with smaller CFL number for everything else equal, in the case of the second order method, as well as in the case of the first order method. In the first order method, we have more numerical diffusion. In the second order method, we have more numerical dispersion. Okay? So that's Lax-Wendroff. Anything else about this? Okay, no. That's it. There are more oscillations, and they're more pronounced as the CFL number decreases.